Hello and welcome everyone to section 12.3. This is the final section that we will be studying in Math 1080, so you guys have almost made it. Just one more lecture to go. Alright, so let's just go ahead and jump into it. Section 12.3 is about calculus and polar coordinates. Remember in section 12.2, we discussed what polar coordinates were, how to graph them, how to look at different functions, that kind of thing. In 12.3, we're going to be looking specifically at the calculus behind polar coordinates, and there's quite a few things to study. So let's just go ahead and look and see what sort of things we can do. First of all, in this section, we are only going to work with polar functions that are specifically of the form r equals f of theta. So r, the radius of the function, is equal to some function of the angle. So the angle, or the radius, will change as a function of the angle. So, for example, we might consider functions like r equals sine of theta plus cosine of theta. In this case, the sine of theta plus cosine of theta would be your f of theta. Or we could consider something like r equals negative e to the theta plus 2 cosine 2 theta. Stuff like this. But we are not going to consider things like r squared equals 2 natural log of theta, because this is not of the form r equals f of theta. And we won't consider things like r equals 2 to the r plus 5 theta. Once again, this cannot be simplified to be of the form r equals f of theta. So the first thing that we're going to try and talk about is the formula that gives us the slope of a tangent line. So in other words, we're going to try and calculate dy by dx. So one common mistake is that since our function is written as r equals f of theta, it might be tempting to think that the derivative dy by dx is equal to f prime of theta, but it's not quite that easy. That is not correct. Remember that dy by dx is the rate of change of y with respect to x. So in other words, it is the slope of your tangent line. It is not just the derivative of this function. Alright, so with that in mind, let's explore this a little bit more. Since r is equal to f of theta, we can write the equations for x and y as follows. So let me switch some colors up. We can write that x is equal to f of theta. I'm going to use the thicker marker. F of theta times cosine theta. Basically, all we did was we replaced this r with f of theta. And we can similarly write that y is equal to f of theta times sine of theta. Alright, so now what you'll notice is that x and y are both written as functions of a single variable theta, right? It's some function of theta here times cosine of theta, and some function of theta here times sine of theta. So that means that these are parametric equations. Remember that a parametric equation in general requires that we write x is equal to f of t and y is equal to g of t. Well, in this section, we essentially have that, except our t, instead of writing t, we would write theta. And so, instead of working with t's, we have theta. So these are parametric equations. So everything we learned in 12.1 now applies to the stuff in this section. Remember, this is only based on the assumption that r is equal to f of theta. If that is not the case, then we have some more difficulties. So from section 12.1, we can now use the equation that actually computes our derivative dy by dx. And the idea is that dy by dx is equal to dy by d theta divided by dx by d theta. Hopefully you remember this. And so all we have to do is calculate the derivative of y with respect to theta and the derivative of x with respect to theta. So since x is equal to f of theta cosine theta, we're going to take the derivative of that. And y is equal to f of theta sine of theta, we'll take the derivative of that. So the derivative of this guy with respect to theta is, since it's a product of two functions, we will have f prime of theta times the second function, sine of theta, plus f of theta times cosine theta. That's derivative of the second part. Divided by, on bottom, we will have f prime of theta times negative sine of theta. Whoops, nope, that's wrong. F prime of theta times cosine theta. And then plus f of theta times negative sine of theta. So let me just change this plus to a minus. And so this is the formula that will give us the derivative of, or will give us the slope of the tangent line at any point theta. All right. So with that in mind, let's look at the book's definition. So we're going to let f be a differentiable function at theta naught. So theta naught is the point at which we want to find our slope. So the slope of the line tangent to the curve, r equals f of theta, at the point f of theta naught is this guy. So this is basically the same thing, except now we replace a theta naught instead of theta. So one thing to note here, and it looks a little bit weird, we have f of theta naught and theta naught in this sort of ordered pair. Normally, you're probably used to seeing stuff like x, comma, f of x, right, as the ordered pair. But in this case, since r is generally the first coordinate whenever we talk about polar coordinates, and theta is the second one, that's why we have f of theta naught r, comma theta naught. And so this derivative works provided that the denominator is non-zero at the point. At angles theta naught for which f of theta equals 0, f prime of theta is not 0, and cosine theta is not 0, the tangent line, so basically if you just plug in all of these conditions into this formula, what you're going to conclude is that the tangent line is this thing with a slope of tangent theta naught. So this is a little bit extra information. You don't really need to know this. You can always just rederive it if you need to. Alright, so one thing that's common to ask of people is to find the vertical tangent lines and the horizontal tangent lines. So recall that a vertical tangent line occurs whenever the numerator of dy by dx is not equal to 0, but the denominator is equal to 0. And conversely, a horizontal tangent line occurs when the numerator is equal to 0, and the denominator is not equal to 0. So if both the numerator and the denominator are 0 at some point theta naught, then the slope at that point, so let me write over here, this is the slope at the point f of theta naught, comma theta naught, is equal to a limit as theta approaches that number theta naught of f prime of theta sine of theta plus f of theta cosine theta divided by f prime of theta cosine theta minus f of theta sine theta. So basically the idea is you just have to compute a limit now as theta approaches theta naught. And perhaps you might need to use L'Hopital's rule or something to figure out what that limit is equal to. Alright, great. So let's continue. let's do this example. We're going to find the slopes of the tangent line to the circle defined by r equals 10. And we're going to express our final answer in terms of theta. Alright, so let's just copy down the formula once again. We know that dy by dx, the slope of our tangent lines, is equal to f prime of theta sine of theta plus f of theta cosine theta divided by f prime of theta cosine theta minus f of theta sine theta. Alright, so one thing to note here is that our function f of theta in this example is 10. Right? Because we always have r equals f of theta. So this is actually a constant function. There is no theta in this function here, but that's okay. We can still work with that. So if f of theta is equal to 10, then that means that f prime of theta, the derivative of this function with respect to theta, is just 0. Which means that this entire term and this entire term are just 0. And so all we are left with, if we plug everything else in, is 10 times cosine theta divided by negative 10 sine theta. And simplifying this, we get negative cotangent of theta, because that's cosine over sine. Alright, and so basically the idea is that for the circle that we would get if we were to consider r equals 10, so let's just draw it quickly. This circle with the equation r equals 10, the idea is that at the angle, let's say pi over 2, so here's the angle pi over 2, we should expect a slope, a tangent line slope, of 0. So let's just test. Negative cotangent of pi over 2. Well, this is just equal to negative cosine of pi over 2 divided by sine of pi over 2. Clearly, cosine is 0 at pi over 2, and sine of pi over 2 is 1, so we get 0 as desired. So that makes sense. That's a good test. And we can also plug in any other value for theta that we wanted to. If we wanted to plug in, say, 3 pi over 4, which is right here, that should give us a tangent line slope of 1. So that's 3 pi over 4. So let's just go ahead and do that. Negative cotangent of 3 pi over 4. This is going to be negative cosine of 3 pi over 4 divided by sine of 3 pi over 4. And cosine of 3 pi over 4 is negative root 2 over 2. And sine of 3 pi over 4 is positive root 2 over 2, which of course gives us an answer of 1, which is what we expected just based off of the picture. The slope here is clearly 1. So let me say dy by dx equals 1, and up here dy by dx equals 0. So this should be a fairly good example to illustrate the idea behind calculating dy by dx. Alright, but we can certainly make our problem more complicated, so let's try a different example. We're now going to find all of the points on the interval between negative pi and positive pi at which the cardioid, defined by r equals 1 minus cosine theta, has a vertical or a horizontal tangent line. So recall that a cardioid is something that will look like this. It kind of looks like that butt shape. It might be rotated depending on exactly which cardioid you're working with. So perhaps it's one of these. Oh, that's a terrible one. But that's the general shape of a cardioid. So let's go ahead and calculate the tangent line slope. So dy by dx, once again, we're going to write out that it's f prime of theta sine of theta plus f of theta times cosine theta divided by f prime of theta cosine theta minus f of theta sine of theta. Alright, so in this case, our f of theta is the function for the cardioid. It is 1 minus cosine theta. And f prime of theta, if we take the derivative of this, will be sine of theta. Alright. Alright, so this calculation will get a little bit messy, so just hang tight with me. If we plug in everything, we have f prime of theta, which is sine of theta, times sine of theta. F of theta, of course, was just 1 minus cosine theta, times cosine theta. F prime of theta is sine of theta, times cosine theta. Also, if you don't care to see the details on this, feel free to skip ahead to when I actually have written all this out. Might be a good exercise to go over, though. Alright, so from here, what we can do is we can just go ahead and distribute everything. We have a sine squared of theta here. We're going to write that as 1 minus cosine squared. You'll see why in a minute. So 1 minus cosine squared of theta. And then we're going to distribute these two together. So we're going to get cosine theta minus cosine squared of theta. So the reason that we did the sine squared and the cosine squared thing was so that way we could combine this cosine squared and this cosine squared. On bottom, we have sine of theta cosine theta. So we can just keep that as is. Minus sine of theta. And actually, what I want to do is I actually want to factor out this sine of theta from both terms. So I'm going to have sine of theta times cosine theta minus 1 minus cosine theta. Alright, so simplifying the numerator, we're going to end up with 1 minus, let me actually rewrite it a little bit differently. We're going to have negative 2 cosine squared theta plus cosine theta plus 1 divided by, on bottom, we have sine of theta times 2 cosine theta minus 1. Alright, and we actually can factor the numerator as well. Notice that this numerator can essentially be written as 2u squared minus u minus 1 if we factor out that negative. Alright, where the u is cosine of theta. And so if we factor that, we can write it as negative let's see, what do I want to do? I want to write this as negative 2u plus 1 times u minus 1. Okay, let me make sure that makes sense. Get 2u squared plus u. Yeah, that looks good. Alright, and so with that in mind, we can rewrite this entire numerator as negative 2 cosine theta plus 1 times cosine theta minus 1 divided by, and on bottom we have sine of theta and 2 cosine theta minus 1. Alright. And so if you're fast forwarding, you should stop fast forwarding. The thing to notice here, the reason I cared to do this sort of simplification is because in order to find vertical and horizontal tangent lines, I need to notice when the numerator is 0 and when the denominator is equal to 0. That is really difficult to do if I just leave it like this, or if I just leave it like this, for example. I need to factor the numerator and the denominator as much as I can to make this a more promising problem. All right, so I have essentially done that here. We have factored the numerator, we have factored the denominator, and now I need to figure out when the numerator and denominator are equal to 0. All right, so let me do that down here. I'm going to keep this visible. So when does the numerator equal 0? And remember that theta is between negative pi and positive pi. Alright, so the numerator is equal to 0 when either piece is equal to 0. Okay, so the first possibility is that 2 cosine theta plus 1 equals 0. And if we solve that for cosine theta, we get that this occurs when cosine theta is equal to negative 1/2. And that occurs when, alright, so when is cosine of theta equal to negative 1/2? That occurs at theta is that right? Theta equals plus or minus 2 pi over 3. Let me think about this for a second. Cosine of theta. Yeah, so the unit circle, the cosine of theta, that is equal to negative 1/2. Oh, right, this is negative pi to positive. Okay, sorry, I was getting confused. So, yeah, negative 1/2 would occur at these two angles, which is plus or minus 2 pi over 3. Right, okay. So, yeah, that's when that occurs. Ooh, sorry, had a brain fart there. All right, so cosine of theta is equal to... Also, the second possibility when the numerator can be 0 is when this term is equal to 0. So that occurs whenever cosine of theta is equal to 1. And of course, that one occurs whenever theta is equal to 0. So let me just box each one of these possibilities in. We will use those in a minute. Alright, so that's when the numerator is equal to 0. When does the denominator equal 0? Alright, so the first possibility is that this occurs whenever sine of theta equals 0. That occurs only when theta equals 0, pi, or negative pi. So we can say 0 or plus or minus pi. Alright, so 3 possibilities for whenever sine of theta is equal to 0. The second circumstance when the denominator is equal to 0 occurs whenever 2 cosine theta minus 1 equals 0. That occurs only when cosine of theta equals 1/2. And that means that theta will have to be plus or minus pi over 3. Alright, so using all of this information, we have the following. Let's use a green. We have horizontal tangent lines occur whenever the numerator is equal to 0 and the denominator is not. So the numerator is equal to 0 at these values for theta. And you'll notice that the denominator is not equal to 0 at plus or minus 2 pi over 3, but it is equal to 0 at 0. Notice that the numerator and denominator are both equal to 0 at theta equals 0. So we will discuss what happens there in a second. But we do know that a horizontal tangent line will occur at theta equals 2 pi over 3 and negative 2 pi over 3. Alright, and a vertical tangent line occurs when the opposite is true, whenever the denominator equals 0, but the numerator does not. So, it will equal 0 at 0 plus or minus pi and plus or minus pi over 3, as we already discussed. At theta equals 0, both numerator and denominator are equal to 0, so we will have to reconsider that in a second. But we do know for certain that a vertical tangent line will occur at plus or minus pi. Let me write out the terms in their entirety. So minus pi, positive pi, minus 2 pi over 3, minus just pi over 3, and positive pi over 3. But then the question arises, what happens when they're both equal to 0? Whenever the numerator is equal to 0 at a value and the denominator is equal to 0 at a value. In that case, we discussed that you must compute the slope using this limit. In this case, our theta naught is 0, right? Because at theta equals 0, both the numerator and denominator are 0. So, to compute the slope at theta equals 0, we I guess I'll say compute again. We compute the limit as theta approaches 0 of our fraction, which was sorry, I've already lost it. It was 2 cosine theta plus 1 times cosine theta minus 1. I guess we had a negative here. Alright, divided by sine of theta times 2 cosine theta minus 1. Double check that. Yeah, that looks good. Okay. So in order to compute this limit, what you might notice is that if you were to just straight up plug in 0, you would get the indeterminate form 0 over 0. And so that suggests that L'Hopital's rule would work. So if we use L'Hopital's rule, and I won't bore you with the calculations here, let me just go ahead and skip to what the L'Hopital's rule would give us. We would get the limit as theta approaches 0. The numerator would be sine of theta minus 4 sine of theta cosine theta divided by cosine theta minus 2 cosine squared theta plus 2 sine squared theta. And now, if we attempt to plug in 0, let's see what would happen. Sine of 0 is 0. This is 0, so on top we would just get 0. This is 1, and then we would get 1 minus 2 plus 2. Or sorry, plus 0, because this is 0. So we get 1 minus 2 plus 0, which gives us just 0 over negative 1, which of course is just 0. That is not an indeterminate form. And so this suggests, since we got 0 as an answer, there is a horizontal tangent line at theta equals 0, because the slope was 0, right? We computed that the dy by dx is equal to 0, so that means that it is a horizontal tangent line at that point. And if we look over here at the right at our graphic, we will see a picture that confirms our findings. So at pi over 3, right here, the slope is vertical, so there's a vertical tangent line. At negative pi over 3, there is also a vertical tangent line. And at theta equals pi and negative pi, there is also a vertical tangent line. And that is all of the cases when we said that that would occur. At theta equals 2 pi over 3, that is this guy, there is a horizontal tangent line. At theta equals negative 2 pi over 3, there's a horizontal tangent line. And one that might be harder to see is that at theta equals 0, the slope is 0. That is this point. So it may not quite look like it, but right at this point, whenever we have the curves like confining to the origin, we actually do get a slope of 0. And so that gives us a horizontal tangent line there as well. Alright, so that was a heavy example. Lots of trig to know there. But the basic idea is that the horizontal tangent lines occur when the numerator is 0, denominator is non-zero, and vice versa for the vertical tangent lines. Okay, great. So now let's take a look at a different concept. We're now going to look at the area of regions in polar coordinates. So this brings us back all the way to about chapter 6, whenever we were talking about the area within regions of general Cartesian functions. Alright, so the definition is as follows. If R is the region bounded by the graphs R equals f of theta and R equals g of theta, between the bounds of theta equals alpha and theta equals beta, where f and g are continuous, and f is greater than or equal to g, which is a greater than or equal to 0 on this alpha beta, then the area of our region is given by this thing. All right? So the integral will be from alpha to beta of 1/2 times the outer function squared minus the inner function squared. So yeah, let's make a mention here. F of theta is the outer function. And g of theta is the inner function. And it might seem a little bit weird to call these functions outer and inner. Like, what do we really mean whenever we are talking about that? If you take a look over at this picture to the right, perhaps this will give you a good conceptual idea of what outer and inner mean. In this case, the outer function is this f of theta, and the inner function is this g of theta. So more formally, here's the idea. If you want to determine which function is outer and which one is inner, roughly speaking, the one that is farther from the origin is your outer function. The function that is farther from the origin is your outer function. So if I draw a line through my region, so this is my region R, the first function that I contact is g of theta. Therefore, g of theta is my inner function. So when I'm just about to enter my region, the one that I contact first is my inner function. The one that I contact when I am leaving the region is my outer function. So that's my f of theta. All right, and so that's kind of the way that we think about it. These lines that we draw from the origin through our region are called radial lines. And so if you ever hear me refer to a radial line, that's what I'm talking about. All right? And so, yeah, the function that we use to calculate the area is that we have to square the outer function, and we subtract the square of the inner function, and multiply the whole thing by 1/2. Let's do an example. We're going to find the area for one leaf of the following 4-leaf rows given by r equals 2 cosine 2 theta. A picture of this rose is over here on the right. So if you take a look, we are attempting to calculate the area of just this piece of the rose. So the first thing that we would have to do is we have to figure out the bounds for theta that will give us this rows of the function. The picture might give it away already, but we're going to figure out a more concrete way to do this if we weren't given a picture. So the first step in doing a problem like this is to find the angles where the radius is equal to 0. All right. So you'll notice, for example, at theta equals pi over 4, this radius is equal to 0, right? Because if you were to draw a line straight out, you would never contact your region, so the radius is 0 here. Without a picture, the way that we would do this is as follows. We need to write 0 equals 2 cosine 2 theta and solve for theta. So we're going to divide both sides by 2. We would get 0 equals cosine 2 theta. All right, so we have to now ask ourselves, at what angles is cosine of what angles equals 0? So certainly cosine of pi over 2 is equal to 0. and this can occur plus or minus. At 3 pi over 2, certainly. At 5 pi over 2. And 7 pi over 2, plus or minus. These are all angles, and this goes on indefinitely. These are all angles for which cosine of theta equals 0. So cosine of pi over 2 would be 0. Cosine of negative pi over 2 would be 0. Cosine of 3 pi over 2 would be 0. And since 2 theta is the argument inside of cosine, we say that 2 theta is equal to these angles. This means that if we divide everything by 2, we have that theta must then be plus or minus pi over 4. Or plus or minus 3 pi over 4. Or 5 pi over 4. And this list goes on indefinitely. It continues on forever. These are all angles that if you were to plug in for theta, would make this equation true. Okay. The next thing that you might want to know, a similar question that could be asked, is to figure out the angles where the rose petal is at the edge of its leaf. So each one of these little things is called a leaf, and I don't know if there's a technical term for it, but the edge of the petal up here, you might want to know at what angles that occurs at. So the way that you could figure that out is by setting r equals 2. So what did I write find? When r equals 2, the leaf is at its longest. What angles do those occur at? This won't be terribly useful for this particular calculation, but it could be useful in a future problem. Alright, so if we were to instead do the calculation 2 equals 2 cosine 2 theta, divide both sides by 2, we would get 1 equals cosine of 2 theta. Alright, so that means that 2 theta must equal, alright, so let's think about the values. Cosine of what angle gives us 1? Well, that certainly occurs at 0. It will occur at 2 pi. It will occur at 4 pi, at 6 pi, and it can also occur at negative values, so negative 2 pi, negative 4 pi, or negative 6 pi, and this continues on indefinitely. All right. We also could get r equals negative 2. So it might be worth considering whenever our radius is negative 2. All right, and so this would mean that 2 theta would occur at pi, at plus or minus pi, plus or minus 3 pi, plus or minus 5 pi, etc. And if we solve both of these equations for theta, we would get plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2, etc. And I'll have to give myself a little bit more space here. If we solve this one for theta, we would get 0 plus or minus pi plus or minus 2 pi plus or minus 3 pi, etc. Okay, so what in the world did we just show? Basically, the edges of these leaves occur whenever r is equal to 2 or r is equal to negative 2. So at, for example, theta equals 0, you'll notice that we are at the edge of a leaf. At theta equals pi, that is over here, we're at the edge of a leaf. At theta equals 2 pi, we're actually back at this one. Theta equals 3 pi, we're back at this one. Similarly, when r is equal to negative 2, we're at the edge of a leaf. At pi over 2, we're up here. At negative pi over 2, we're down here. At 3 pi over 2, we're down here. At negative 3 pi over 2, we're up here. And so on and so forth. These values will continue to give the same thing. All right, so the thing that is important for this particular calculation is knowing the angles where r was equal to 0. Step 2 in this process is to figure out let's see, how do I want to write this? We want to use two consecutive angles where r equals 0 for, or where r equals 0 for our integral bounds. Okay, so for example, there are two consecutive bounds for theta that give us one leaf of the petal. So the reason we want two consecutive ones is so that we would get one single leaf of this rose. And so, for example, if we use negative pi over 4 and positive pi over 4, that will give us this leaf of the rose. If we were to instead use pi over 4 and 3 pi over 4, we would get this leaf of the rose. If we were to use 3 pi over 4 and 5 pi over 4, we would get this leaf of the rose, and so on and so forth. Any of those bounds will work. So, for example, you could use negative pi over 4, 3 pi, or regular pi over 4. You could use pi over 4 to 3 pi over 4, or any other choice that you wanted. All right, and so actually doing this, we are going to get the integral from negative pi over 4 to positive pi over 4. I argue that this is the easiest. And to compute the area, we need to write 1/2 times the outer function squared. So let's write f of theta squared minus the inner function squared. In this particular case, notice that if we were to draw a radial line, so a line from the origin through our region, we already start within our region, right? There is no entry point like there was in this example. There was no segment of area where we drew the line and we weren't already in the region. So that indicates that there is no inner function. G of theta is equal to 0. And f of theta is our 2 cosine 2 theta. This is f of theta. So we're going to write that in. We're going to get the integral from negative pi over 4 to positive pi over 4 of 1/2 times 2 cosine 2 theta squared d theta. Alright, and so rewriting this, we can pull the 1/2 and the 4 that we get from 2 squared out front, and so we were going to get 2 integral negative pi over 4 positive pi over 4 of cosine squared 2 theta d theta. Alright, the next thing we do is we notice that this is a function which we can use symmetry to help us out a little bit. So we can use symmetry to notice that if we calculate just half of the area of a petal and multiply it by 2, we would get the full area of the petal. So we're going to calculate half of this area and multiply it by 2. So we get 2 times 2, and instead of negative pi over 4 to positive pi over 4, we're going to do just 0 to positive pi over 4 of cosine squared 2 theta d theta, and this is by symmetry. Alright, so everything that's green there is what I changed. Alright, and if we simplify this a little bit, the way that we compute an integral like this, hopefully you haven't forgotten already, since we have cosine squared of 2 theta, we can rewrite this as 1 plus cosine of 4 theta all over 2 d theta. And if we continue this calculation, we can bring that 1/2 out front, so we're going to get 2 integral 0 to pi over 4 of 1 plus cosine 4 theta d theta, and we can integrate this. We're going to get 2 times theta. Alright, so the integral of cosine of theta is sine of theta, or not sine of theta, sine of 4 theta, and we have to divide by that 4, so we get 1/4 sine of 4 theta, evaluated from 0 to pi over 4. And if we plug everything in now, we're going to get 2 times pi over 4 plus 1/4 times sine of pi, and then minus 0 plus 0. And so this is going to be 2 times pi over 4 plus, so sine of pi is 0, and so we just get pi over 2. And so what we have determined is that the area for just one leaf of this rose is pi over 2. So therefore, the area of the entire thing has to be 2 pi, if we multiply it by 4. Okay, so a lot of little things we did on this example. but the main concept here is to follow these two steps. We're going to find angles where r is equal to 0, and then we choose two consecutive angles where r is equal to 0, use those for your integral bounds, and just plug everything in and calculate it. Okay, let's do another example. We're going to find the area inside the circle, defined by r equals 1, but outside of the cardioid, defined by 1 plus cosine of theta. The picture of that region is right here over on the right. You'll notice that it is shaded. And so we need to figure out the bounds for theta that we need to use. So immediately from the picture, it's evident that the bounds for theta that this region exists in is pi over 2 to 3 pi over 2. So those are my bounds for theta. All right. And so now we should think about what the inner function and the outer function for this region are. So the inner function is the one that my radial line hits first whenever I draw it through the region. So if I were to draw a line from the origin outward, the first thing that I hit is this guy. And that is my cardioid, right? That is the 1 plus cosine theta. So this is my inner function. Whenever I am about to exit the region, the function that I am hitting is the circle. So this is my outer function. And no matter what radial line I draw, if I were to zoom in close enough, there would be a small portion of area where I am not in my region immediately. And so the idea is that my inner function will always be this cardioid, and my outer function will always be the circle. So therefore, the cardioid is my g of theta, and this 1, the circle, is my f of theta. It is the outer function. All right, so with that in mind, let's calculate the area. The area is going to be the integral. Once again, my bounds were pi over 2 to 3 pi over 2. Of 1/2 times f of theta squared minus g of theta squared, d theta. We're going to pull the 1/2 out front. All right, f of theta we determined was 1, so 1 squared is 1. And g of theta squared is 1 plus cosine theta quantity squared. All right, so let's continue that. So we're going to get 1 plus 2 cosine theta plus cosine squared theta d theta. There is this minus sign up front, which we'll distribute to each one of these pieces. All right, let's see. Do I have another slide for this one? No. Okay. All right, so simplifying, we have 1 and a minus 1, so those will cancel. We're going to be left with negative 2 cosine theta negative cosine squared theta. And if we pull the negative sign out front, let's see, what did I do? Right, okay. Yeah, let's just pull the negative sign out front. Pi over 2, 3 pi over 2. Alright, so 2 cosine theta. We can replace cosine squared of theta with 1 plus cosine 2 theta, all divided by 2. And then I'm going to go ahead and skip several steps here, just so I don't bore you with all the calculations. But basically, eventually you should come up with the answer of 2 minus pi over 4. Alright, and so that would be our answer. One thing that you could have done to simplify the calculations a little bit is notice that there is also symmetry in this problem as well, just like there was in the last one. So instead of calculating the integral from pi over 2 all the way down to 3 pi over 2, you could have instead calculated the integral from pi over 2 to pi and doubled this area. That would have also been a viable strategy. Alright, but anyway, the answer to this is eventually 2 minus pi over 4. Alright, great. Let's continue. One thing that we can also do is we can try to find the points of intersection for a polar region. So we are going to find the points of intersection between the circle given by r equals 3 cosine theta and the cardioid 1 plus cosine theta for values of theta between negative pi and positive pi. So in general, the way that we do that is, as you might expect, we're going to equate the r's. And so we're going to write that this function is equal to this function. 3 cosine theta equals 1 plus cosine theta. If we subtract cosine theta from both sides, we get 2 cosine theta equals 1, which occurs if and only if cosine theta equals 1/2. And as we discovered earlier, the values of theta for which this occurs are plus or minus pi over 3. Earlier, we also discussed that, or actually, in general, let me say that, in general, we would consider more values that this could occur at, but since theta is bounded between negative pi and positive pi, we stop here, because the next values for which this would occur would be a full trip around the circle. Alright, and so these are our points of intersection. Theta equals plus or minus pi over 3. But as you have already seen in this glaring red text down below, problems like this will often have hidden points of intersection. And graphing the curves is really the only surefire way to find those. So if we actually take a look at the picture down here, we notice that there is an intersection point here at pi over 3, at theta equals pi over 3. There is an intersection point here at negative pi over 3. But there is also an intersection at the origin. For the cardioid, it's the coordinate 0 pi, and for the circle, it's the coordinate 0 pi over 2. The reason we didn't find these on the original problem was because the radii aren't equal at these values of theta and these values of theta aren't equal for the two different curves. And so since the values of theta aren't equal, it's not going to appear in this calculation. So yeah, there are often going to be hidden points of intersection, ones that can only be found if you actually graph the two functions. And so, yeah, there happens to be one on this example. All right, so now we're going to do another area calculation. The idea here is that we are going to need to find the area of region A, region B, and region C. All right, so the first thing that you should do for each region is you should figure out what the bounds for theta should be. So for region A, the bounds for theta, well, if you just take a look at the picture, you'll notice that it goes from theta equals 0 up through theta equals this value, which occurs at pi over 3. So theta is between 0 and pi over 3. Those should be our bounds. So therefore, the integral is going to be 0 to pi over 3 of 1/2. The next thing you should do is you should think about what your outer and inner functions are. So the outer function is the one that occurs right when this radial line is about to leave the region. So that means that this function is your outer one. And this function here is our circle, right? You see that this function is the circle, and that is 3 cosine theta. So the outer function is 3 cosine theta, and then we're going to square it, and we're going to subtract the inner function squared. And the inner function is the cardioid. It is the 1 plus cosine theta. So 1 plus cosine theta squared, and that's our integral setup. Okay? So then we're going to consider region B. Region B is a little bit more tricky. First of all, if we take a look at the bounds for theta, you'll notice that this starts at theta equals 0, and then it goes up and up and up and up and up and up and up. And then region B also includes this little segment, right? So it's going to go up to here and here, and it actually goes all the way up to theta equals pi over 2. And so the bounds for B will be 0 to pi over 2. But we can't quite use those as our integral bounds. The reason we can't just throw those and say that this is the integral from 0 to pi over 2 of something is because the outer function and the inner function, the outer functions change at a certain value. So notice that if you draw your radial line here, we start in our region, right? There is no point when we are not in the region B. So there is no inner function, but the outer function is the cardioid, right? It's this blue function. It is the cardioid. If we draw the radial line here, it's the cardioid. Here it's the cardioid. Here it's the cardioid. Here it's the cardioid. But once you get to this angle measurement, it starts a transition. Instead of the outer function being the cardioid now, the outer function, if we draw a radial line right here, is now the circle, right? So the idea is that from pi over 3 to pi over 2, the outer function is the circle. So let me write this in words. From 0, let me say from theta equals 0 to theta equals pi over 3, the outer function is the cardioid. But from theta equals pi over 3 to theta equals pi over 2, the outer function is the circle. Okay, and so using this information, we have that the area is equal to a sum of two different integrals. So this is going to be the integral from 0 to pi over 3 of 1/2 times the outer function squared, and in this case it's the cardioid, which is 1 plus cosine theta quantity squared. And then we add the integral from pi over 3 to pi over 2 of 1/2 times the equation for the circle, which is 3 cosine theta squared. Alright, so the area is the sum of those two. Let me actually make them a little bit smaller and put them on the same line. Yeah. Cool. So now for region C, it's still a little bit more complicated. So once again, region C is this portion, in case you can't determine the colors apart. It is this piece. So if we were to draw a radial line right here, what you will notice is that we actually do not start in our region C, right? We start in region B. That indicates that there is an inner function here. It's not just 0 like it was for the second example. So the inner function is this function, which is our circle. So our circle is the inner function, and the outer function is the cardioid. We enter the region C by crossing the circle. We exit the region C by crossing the cardioid. All right? At theta equals pi over 2, there is a change, though. Notice now that if we draw this radial line, we never enter region B, right? We are always going to be in region C if we draw this radial line. That indicates for theta from pi over 2 to pi, the inner function is 0, and the outer function is still the cardioid. Let me write that in words. So from theta equals pi over 2 to theta equals, from theta equals pi over 3, right? That's where it starts, yep. To theta equals pi over 2, the inner function is the circle, and the outer function is the cardioid. And then from theta equals pi over 2 to theta equals pi, the inner function is 0, and the outer function is the cardioid. So I think writing it out, like this, whenever you're doing these sorts of problems, can really be helpful to picture what exactly you're doing. And so finally, the calculation will be as follows. It once again will have to be a sum of two integrals. The first one from pi over 3 to pi over 2 of 1/2 times the outer function squared, which is 1 plus cosine theta, squared minus the inner function squared, which is 3 cosine theta squared and d theta. And then we're going to add the integral from pi over 2 to pi of 1/2. The outer function is the cardioid, so that is 1 plus cosine theta, we square. There is no inner function, and so we may write it just like this. Alright, so that was fun. Those are how we would calculate the areas for 3 different regions in this picture. Alright, the next thing we're going to talk about is the arc length of a polar curve. So the formula for arc length and polar coordinates is similar to the arc length formula that we learned in section 12.1. Remember, that's the Parametric Equations section. So without proof, we're going to provide you the final thing that you will learn this semester, and that is this formula. The length for a polar curve is given by the integral from alpha to beta of the square root of f of theta squared plus f prime of theta squared d theta. All right, so just note that this is the function, and this one is the derivative. So you're adding the function squared to the derivative squared. All right, so let's do an example. We're going to find the arc length of the cardioid defined by 1 plus cosine theta, where theta ranges from 0 to 2 pi. So the first hint I'll give you is to consider its symmetry, and the second hint, which we will use later, is the fact that 1 plus cosine theta is equal to 2 cosine squared of theta over 2. That'll be useful in a bit. All right, so the thing to notice first is that the arc length for the upper half of this thing is equal to the arc length for the bottom half, right? And so we need only consider the arc length for the top half. So we will say that L is equal to, let me just go ahead and write the first calculation that we should care about. It is f of theta squared plus f prime of theta squared d theta. All right, if we plug those in, f of theta is, of course, just 1 plus cosine theta, and that implies that f prime of theta, let me do that up here, is equal to negative sine theta. So 1 plus cosine theta quantity squared plus negative sine theta squared d theta. At this point, we will use its symmetry, and notice that we can write this as 2 times the integral from 0 to pi of the square root of 1 plus cosine theta squared plus negative sine theta squared d theta. All right, so I'm only considering the integral from 0 to pi now. All right, so this is the integral of 2, integral from 0 to pi. And to calculate this, let's just go ahead and expand everything. I mean, what else can we do? We're going to get 1 plus 2 cosine theta plus cosine squared theta. And then over here, we will get plus sine squared theta Well, that's convenient. We have cosine squared theta plus sine squared theta. This is just, of course, equal to 1. And so we get 2 integral 0 to pi of the square root of, so if we add this one and this one, we end up with 2 plus 2 cosine theta d theta. And at this point, we might get stuck. We can factor out that 2 if we really want to. We could write this as 2 integral 0 to pi. Since we're factoring it under a square root, we can write that this is root 2 times the square root of 1 plus cosine of pi, or cosine of theta. But at this point, we might get a little bit stuck, but perhaps you remember that there's a second hint I gave you. 1 plus cosine of theta is equal to 2 cosine squared of theta over 2. And this actually isn't anything new. You guys actually already know this. This is the double angle formula. It's just written with theta over 2 as the argument, right? Because if we wanted to write cosine squared of theta over 2, this would just normally be 1 plus cosine theta all over 2. And so if we just multiply both sides by 2, that's where we come up with that equation. And this actually will help us significantly perform our work here. So let me actually go to the next slide. This is the last slide you're going to encounter in 1080. I hope you're sad about that. You know, it's been a long semester. All right, so we have the integral from 0 to pi of the square root, if we replace 1 plus cosine theta, with 2 cosine squared of theta over 2 d theta. We once again have that square root of 2 we can pull out, so we get 2 square root 2 square root 2 integral 0 to pi. The square root of cosine squared of pi over 2, or not pi over 2, theta over 2, is just the absolute value of cosine of theta over 2. We can rewrite this as just cosine of theta over 2 because between the bounds of 0 and pi, this whole argument will be positive, right? Because cosine from 0 to pi over 2 is always positive. And so we may write that this is equal to 4 integral 0 to pi of cosine theta over 2 d theta. Finally, we can integrate this. This is going to be 4 times sine of theta over 2. We divide by 1/2. And this whole thing is evaluated from 0 to pi. So we have a 1/2 in the denominator. We can make that an 8 on the outside. We would get sine of pi over 2 minus sine of 0. So 8 times, so sine of pi over 2, that's 1. Sine of 0 is 0 for a final answer of 8. We did it, guys. We made it to the end of the semester. All right. That's all I've got for you in this section. If you guys have any questions or anything you want to talk to me about, feel free to let me know. I will likely be doing a review session at some point in the near future, so stay tuned for that. And yeah, until then, that's all I've got for you. Stay safe out there, and let me know if you have any questions.